Chapter 3.1, probability. So we're moving into, we got to talk about the random chance of things happening if we're going to do higher level statistics, right? Remember what stats is all about. Let me keep this before you. What is stats all about? What if doctors come out with a new treatment for cancer, which they think is better than the old one? They give it to 15 patients, and they do a fair bit better than people did on average for the last 10 years with the old treatment. How do we know if the new treatment is really better? If it helped, if it did better, it helped 15 people. How do we know if the new treatment really did that, or what? What am I implying? What else is there? Yeah, the new treatment did better. It's better. What am I talking about? Am I making any sense? Why am I saying this is a problem? You might be thinking, this isn't a problem. What's the problem? You got a new treatment. It helped 15 people. It helped 15 people more than the old treatment that's been around for years and years. Treated thousands of patients. The new one helped 15 people more than the old one. So yeah, the new one's better. What do you mean? We got to make a big deal out of this. No? There's something to be said, isn't there? What is it? Why wouldn't we automatically say, if the new one did better for 15 people, it's the better treatment. Let's buy the $1 million equipment to get the new treatment going and start giving it to hundreds and thousands of people. Forget the old one, take all that machinery out, train all the doctors with the new one, treat all the people with the new one. It's better.
Because it doesn't have statistical significance?
Yeah, it may not, huh? What are we afraid of?
It was too small.
Yeah, we're afraid that was just random luck. You with me? That's like could be a subtitle for this whole course. Statistics, or what about luck? Really, that's it. Right? Couldn't it have just been, it was only 15 people. Couldn't it have just been that they were just healthier people by random chance? Right? They just gave it to 15 people, and maybe they just by random chance happened to select 15 people who were going to do better anyway. Even if you gave them no treatment, they were going to bounce back from the cancer. They were going to heal on their own, and maybe the new treatment's actually worse than the old. Maybe it did nothing, and we just happened to get lucky 15 people. Right? If that's the case, then we better be a little more careful before we spend millions of dollars on new equipment and start treating everybody with a new treatment that's maybe not better than the old treatment. How do you decide that? How do we know if the new treatment, if this was just luck? How do we know if those 15 people that we gave the new treatment to, and they seemed to do better, if that was just a lucky group of 15 people?
If you did a control study.
We got to do some things. What if we did 115 people and they still did better? Do you think that's random luck? Doesn't it feel less likely? Right? I'm just going for your feelings here. That's the main thing you're going to remember from this class. The specific calculations you may never do. But I'm thinking, what are you going to get out of this class 10 years down the road in your life with a professional job, reading statistical things? It's the main deep feelings. Those are what's going to stay with you. Do you feel it? If you only did 15 people with the new treatment, that could be just a lucky group of 15. And the new treatment's not really better. Who knows? But if you did 115, there's no way that's luck. That new treatment is working, because the issue is anything in life, it either happens for one of two reasons. Anything in life happens because of random chance, luck, or something causes it to happen. Right? You with me on that fundamental idea? Everything that happens in life happens for one of two reasons. Random luck, random chance, or something causes it to happen. So when we give a treatment to only 15 people, we're afraid that might just be random chance. Maybe the new treatment isn't really causing more health. But if you give it to 115 people, there's virtually no way that you got lucky 115 times in a row. We start to believe that new treatment is really doing something. That can't just be chance. The new treatment is really causing more health. Now, what's leading us to that conviction? What is that feeling in your gut or your head or whatever that's leading you to feel that? 115 people, the probability is crazy low that you're going to get 115 people by random luck, right? Whereas for only 15 people or 10 people, you feel that you might be able to get lucky on 10 people. So it's all about probability, isn't it? It's all about the chance of that happening. That's why we need to study probability, because that underlies statistics. It's all about what's the chance that we got a lucky 15 people? What's the chance that we got a lucky 115 people? Obviously, not very good at all, which gives us confidence that the new method is really working. So it's all about probability. Probability is the ground of what we do in statistics. All right, so with that, let's study a little probability. What do you think about probability? What do you think about these statements here? If let me just give, before I get into, you can read them as we go. If I roll a die, let me just say, or let me flip a coin. What if I flip a coin? I don't have a coin with me. I'll bring a coin in a week or two. If I flip a coin, what's the chance I'm going to get heads? 50. Yeah. So 50% chance, right? Probability is, you can say 0.5, or you can say 50%, or you can say 1/2. Those are three languages to say a part of a whole, aren't they? Right? Decimal, percentage, and fraction. They're all saying the same thing. And it's like me saying one, uno, or one in some other language, right? I'm saying the same number in three different languages. This is the same portion, part of the whole, in three different languages. And they all are the chance of getting a heads when you flip a coin. So let me ask you this then. If I flip the coin twice, how many heads am I going to get? How often does heads come up? Half the time. So if I flip twice, how many heads am I going to get? For sure? Right. We all sense it, huh? Yeah, kinda, but nah, not necessarily, huh? Probability is kind of a slippery thing, isn't it? We say it's going to happen 1 out of every 2 times in general. But that doesn't mean if you flip twice, exactly 1 out of those 2 will be heads. It is possible to get 2 heads in a row. We all know that. Or 2 tails in a row, isn't it? So then, what do we even mean then? What do we mean by saying the probability of heads is 1/2 or 50% or 0.5 if we also know that you're not for sure going to get 1 out of every 2 heads? What do we even mean then? Why are we even saying it's 1 out of 2 if it isn't really 1 out of 2? Right. It's all about likelihood, isn't it? It's all about likelihood. And let me ask you this. If I was to flip the coin 100 times, how many heads do you think I would get if I'd flip 100 flips? How many heads do you think? About 50 heads. Now, again, it's not going to be exactly 50 heads. It might be 48 or 49 or 51 or 52. But it's probably not going to be 99 heads. In fact, it's very unlikely, we'll calculate that later, that you're going to get 99 out of 100 heads. It's super unlikely, isn't it? If your friend tells you that he flipped a coin 100 times and got 99 heads, you would be more wise to believe your friend is lying or insane than to believe that your friend really did that. It's super unlikely. So, and we'll get into all that probability. So, the point is, probability shows its face, its real truth, its real power, as you do something a lot of times, not a few times. Right? You sense that, huh? You feel that. I want to drive that feeling strong because it's a right feeling. It's a good feeling you have. If I was just to roll a die 2 times or flip a coin 2 times, I very well likely might not get 1 head, 1 tail. Not too many. It wouldn't amaze you if I said, hey, I flipped twice and I didn't get any heads. Or I flipped twice and I got both heads. It wouldn't amaze you. But if I said I flipped 50 times and they were all heads, that would amaze you, wouldn't it? So it's the law of large numbers that really become the power behind probability. The probability doesn't happen just when you do something once or twice. But as you do something 100 times or 1,000 times, then you see that there actually is a law there governing it. And I'm hoping a couple nights I'll bring some dice, we'll roll some dice, and we'll put them all up as a class, and we'll see that happen. When each of us is rolling, 20 times 20 groups, 400 rolls, and we make a big spreadsheet on the screen, we'll see that in the large scheme, probability laws are true. So that's what this question is. I'm probably going on way too long. What am I doing? It's 15 minutes on number 1. I'm not doing one very well. I like probability. I want to talk too long about it. Anyway, let's read which of these is true. So, always has a predictable pattern both in the short run and the long run? Not so much. Not the short run. Is unpredictable in the short, but has a predictable pattern in the long. Yes. So, probability is predictable only in the long run. They call that the law of large numbers. Meaning that if you do something a whole bunch of times, large numbers, you do it 100 times or 1,000 times, you'll see the laws of probability occur. But if you only do something 2 or 3 or 4 times, anything can happen, right? All right, so I think you sense that. Cards here. Special deck of cards has 5 green, 3 yellow. The green cards are 1, 2, 3, 4. So here, let me write this out for you, orderly like. There's a green 1, a green 2, a green 3, a green 4, and a green 5. And the yellow are 1, 2, 3. So there's a yellow 1, a yellow 2, and a yellow 3. Some weird cards. So anyway, here come the questions. So how many elements are there in the sample space? Sample space is, let me write that down here for you. Sample space is all possible outcomes. Let me just put it that way. So how many different things can happen? How many possible items are in our sample space? There's 5 green cards, 3 yellow cards, 8 altogether. We're just saying there's a total of 8. So like if I roll a die, that has 6 sides. That would be 6 things that can happen. If I flip a coin, that would be heads or tails, 2 things that can happen. Make sense so far? So sample space is just the list of all the outcomes. Now, PE, what in the world's that? P means probability. And E, what is E? Well, up here, you got to look for what they did E. Even number. So when they ask me for P parentheses E, what they're saying is, what's the probability that if you grab a card out of the deck, that you're going to get an even number? Even number. Well, how many, here's the cards, we're looking at the 8 cards. How many even numbered cards are there? The 2, the 4, and the 2, the yellow 2, huh? Yeah. So then the other ones are odd, right? So if I grab one card out of the deck, what's the probability I'm going to get even? How does probability work? It's the number that you want of whatever you want to happen over the total number, right? So what is the number of things that I want? I want to get an even card. So 3 out of how many total things could happen? Out of 8, right? There's 8 cards. So 3 of the 8 cards are even numbered cards, aren't they? So the probability, the chance that I'm going to get an even number is 3 out of 8. And they want a decimal. So if you divide that in your calculator, just go 3 divided by 8, you get, isn't it 0.375? So that's what they want. They say it round to 4 places, but it doesn't go 4 places, so 0.375. How we doing? This making sense? On that, so probability is just part over whole. Part over whole. All right. So there's a whole deck of cards. If you're somewhat unfamiliar with the deck of cards, that's kind of nice. There it is. As shown above, a classic deck of cards, 52 cards, 26 black, 26 red, blah, 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 blah. If you select a card at random, find the probability of getting an 8 of hearts. So in days to come, I'm going to try to give you the probabilities for all kinds of gambling games. and show you exactly. We're going to actually calculate probabilities like they do in the casinos and insurance companies, which is legalized gambling. And I'll explain how that is and how they calculate where to set their rates and casinos, how to set their betting amounts. It's all calculated. It's a science. They know exactly what's going to happen. Nobody wins at gambling. Nobody wins. If they tell you they're winning, they're either cheating the system somehow, which they don't let that anymore. They got everybody watching everything. Or they're just living in a fantasy world. Or they only went twice. If you go regularly, law of large numbers, you will lose. Absolutely. It's a science. So, 8 of hearts. So what's the probability of getting an 8 of hearts out of a deck of cards? Yeah, there it is right there. There's the 8 of hearts. It's 1 card out of how many in the deck? Yeah, if you up here it says 52. 52 cards. So if you're playing poker, if you know anything about it, and you're drawing to a straight flush and you need the 8 of hearts, your chances are low. 1 out of 52 to pull the 8 of hearts. Okay, next, what's the chance of getting a diamond or a club? So what if you're like, I just really want to get a diamond or a club? What's the chance? Well, how many diamonds are there? Yeah, all of these are diamonds. And where's the club? Oh, clubs? Clubs is up here. All of those are clubs. Yeah, so there's 13 plus 13 out of 52, 26 out of 50. If you reduce that fraction, guess what it is? A half, huh? It's a half. Oh, actually, they want a decimal, don't they? Yes. So divides, so it's going to be 0.5. Oh, I forgot to get a decimal on that other one. What is 0.52 as a decimal? Well, 1 divided by 52. Yeah, they want and they want, what? How many? 4 places? 0.0192. Yeah, that's actually the answer they wanted here. This one's 0.5. You can see that half the cards are clubs or diamonds, aren't they? So it makes sense. The chance of getting clubs or diamonds is half, 0.5. You good so far? How about C? A number smaller than 6, counting the ace as a 1. So what if you're drawing to a straight, and you're like, I really need a number smaller than 6. Let me give a fresh screen here. So if you need a number smaller than 6, I'll bring it up here. Smaller than 6. So what numbers are smaller? Ace is being counted as a 1. That's what they say that down here. So they don't always count ace as a 1 in all card games, but they're saying to do so in this game. Ace, 2, 3, 4, 5, not 6. So I don't include the 6 because it's got to be smaller than 6. So I want to get an ace, 2, 3, 4, or 5. How many cards are ace, 2, 3, 4, or 5? Yeah, all. Whoop, I'm going to go too far, huh? Right there. All of those cards. And that's how many? That's 5, 5, 5, 5. 20 cards. 5, 5, 5, 5. That's 20 out of, again, 52. That's a funny looking 5 down there. 20 out of 52. Whatever the calculator says. 0.3846. So that means if you're playing cards and you want to get an ace through 5, the probability that you're going to do that is 38% chance. That's the chance that you're going to be able to do that. You'll be able to calculate the probability for all these kind of games. We good? Questions? So number 4. A group of people were asked if some people see the future in their dreams. 413 responded yes. So 413 people said yes, I think some people see the future in their dreams. 476 said no, I don't think they really see the future in their dreams. Find the probability that if a person is chosen at random, the person believes that people can see the future in their dreams. So what's the probability, if you grab one person at random, that they're a yes person, basically, is what they're saying. That they're a person that believes people see the future in their dreams. What's the chance of that? So remember, it's always part over whole or total, huh? So the yes part is 413. The total is whatever those add up to be. Is it 9 even? 900 even? 413 out of, oh no, it's 890? Oh, it is? Hey, no, 8, I can't do it. 889, is that right?
Yeah, that's fine.
Okay, good. So, I'm just guessing a little bit, I don't know. 413 divided by 889, so I'm getting 0.46, how many places? 4? 456, so it rounds to 6. 0.4646? We good there? So if you grab somebody at random, the chance that they believe people see the future in their dreams, 46% chance. Just under half of the people. And that makes sense, right? 413 is just a little bit less than half of people believe that's the case. Good. Questions? Cards. Then it would be blackjack. But nobody can, very few people can count cards out of a 6-shoe deck, which is what they do now. All right, so if you roll 2 dice, there's everything that can happen when you roll 2 dice. How many different, you could get a 1 and a 1. They call that? Snake eyes. What did you say, bullseye? And a 2 and a 1, a 3 and a 1, a 4 and a 1, a 5 and a 1, 6 and a 1, or a 1 and a 2 and a 2, blah, 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 blah. All the way down to 6 and 6, which they call? I'm waiting for you, no? No. Boxcars. All right, anyway. So there's, how many different things can happen here? How many total different results are there? How tall is this? 6 by 6? 6 by 6? 36 things, huh? 6 rows, 6 columns. It's 36 possible outcomes when you roll 2 dice. Now they're saying, what's the probability? Oh, it's off the screen. They want the probability of getting a sum of 7. I believe, isn't that what they said? Let me change this. So they want the probability that you're going to roll 2 dice and get a sum of 5. So what's the chance when you roll 2 dice that they're going to total 5? Well, I'll start with the denominator. That's got to be 36, right? The bottom's always the total. So on the top, we got to figure out how many of those results. Can anybody see even one result up there that totals 5?
2 and 3.
Yeah, right there, 2 and 3. That's a total of 5. 4 and 1, yeah. 3 and 2. 1 and 4. Look at how they sit. They're all in a diagonal. All the ones that sum to be 5 are in a diagonal. Look at the next diagonal. What do all those sum to be? See how they all sum to be 6? What is the main diagonal all sum to be? 7, etc. Never seen that before? The sums go in the diagonals. So what's the most likely sum when you roll 2 dice? What's the biggest diagonal? 7. Anyway, I'm getting into too many questions. We'll do that later. So what's the probability of rolling 2 dice and getting a sum of 5? 1, 2, 3, 4 different ways to do that. 4 out of 36. Divide that in your calculator. I think you get 0.1111, don't you? So about 11% chance, if you roll 2 dice, of getting a sum of 5. That makes sense? So that's how they calculate everything in the craps world. They know all those probabilities. It's a science. They've got it all worked out. Good so far? This making sense? Accidents. Okay, so let's big table, probability table about this. So here's what happened. Let's make sure this table's making sense for you. Tell me about these 44 people. These are all people that were in some kind of an auto accident or death, pedestrian deaths. Table summarizes results from pedestrian deaths that were caused by automobile accidents. This is serious business. Okay, so what happened with these 44 here? Yeah, they were both intoxicated, right? Pedestrian was intoxicated. Driver was intoxicated. So in 44 of the accidents, or deaths, in 44 of the pedestrian deaths, both the pedestrian and the driver of the car. So, I don't know, the pedestrian maybe just wandered out into the road. He or she was drunk. The driver was also drunk and got hit and died. So 44 people died, this table is saying, because they were drunk and the driver was drunk, right? So tell me about the 277. Those 277 that died, what was the case?
The driver was not.
They were drunk, but the driver was not. So probably they did something crazy out in the middle of the road. The driver did not. I mean, the rest we can only guess at, but they were drunk, the driver was not. Make sense? What about this 79? What's the story with their deaths? Yeah, driver was a yes drunk. They were not. The pedestrian was not drunk. So the driver probably did something crazy. And what about those 577? Nobody was drunk. It just happened for some reason other than drinking. All right, so now here comes the question. So if one of the pedestrian deaths is randomly selected, find the probability, oh, it's off the screen, that the pedestrian was intoxicated. Okay, so let me just write it over here. So the probability, if you grab one at random, so we're just going to grab one from this group of all these pedestrian accidents, pedestrian deaths in an auto accident, grab one at random. What's the probability that the pedestrian was intoxicated? That's what they're asking. What's the probability that the pedestrian was intoxicated? How are we going to figure it? We know probability is part over whole or total or whatever, right? So, So what's the out of this? Well, here, let's start with the denominator. Well, I don't know where to start. So what's the part? How about let's just start with the top. What's the part? How many pedestrians out of all these people that died in an accident? How many pedestrians were intoxicated? Yeah, these added up, huh? We just got to add those up on our calculator, right? We were that, whatever that is. I'll do it on my calculator too. 277 plus 44. I'm getting 321. 300. So 321 total intoxicated pedestrians. You with me on that? And then let's add these up too. You'll see why in a minute. Let's just add those up. 77 plus 577. I'm getting 656. So 656. These are the totals, aren't they? These are the totals. So there's a total of 321 pedestrians that were intoxicated and died in an accident. There were 656 pedestrians who died in an accident and were not intoxicated. So how many total pedestrians were there? Whatever these added up is, right? 321 plus 656. I'm getting 977. Everybody seeing that? So that's my denominator. Let me pause there for a second. Does everybody see what I did? They're asking me, if you grab one person at random out of this group, well, that's 977 total people. What's the chance you're going to get a pedestrian that was intoxicated? There's 321 intoxicated pedestrians. So the chance is 321 over 977, whatever the calculator says. And that comes out to be 0.3286. When you round to four places, 0.3286. Is that making sense? How I did that? Now, if I was you, I'd be wondering, no, wait a minute, what if we added up like the numbers on the right? Could we do that? Do we need to? You could. You don't need to, but you could. Let's do that, though. I think that'll be instructive for you. It's not required, but it's certainly not wrong or anything. So what if you added these two up? Let's do that in our calculator. So we'll do the side totals as well. That'll be the totals over here. So that, in general, that's what I would encourage you to do with these tables. Just get the totals on the bottom, the totals on the side, and they'll both add up to the same thing in the end. I'm getting 123. And then add these two up. It's going to be a big number. I'm getting 854. This is actually not required. And if you add these two up, guess what you're going to get? 977, that same total. So you don't really need to do that, but you could. Then you have all the data before you. Is that making sense? And then you go, okay, 977 total, complete. If you add, or you can just add up all 4 boxes. It'll be 977. Is that making, there's a lot of ways to get to these numbers. Is that making sense how I got the 977? Just all 4 of these boxes added up. That's the total number of people in this table. And then how many were intoxicated pedestrians? Pedestrian, intoxicated, yes. It's these 2, which add to 321. Is that good? Questions I can answer? Yeah.
I'm confused, like, how you got the, like, how to read the
let me try to help. So I'm just looking at the different column and rows coming together. So like these 44. So that's a good question. I'm sure that many people are kind of thinking the same thing. So let me help out. So like when I'm looking here at this 44, so I'm looking at the yes and the yes. That's where the yes and the yes come together. So that means pedestrian intoxicated, yes. Driver intoxicated, yes. So these 44 people that died in an accident, in their accident, the pedestrian was drunk and so was the driver. And then like for these 79 here, the pedestrian was not intoxicated, but the driver was a yes on that. Good. Other questions? All right, let's try them. Okay, so grades versus gender. So there's some test that was given, and 16. Tell me about those 16 people right there. What do we know about those 16 people? They were males who got A's on the test. Tell me about these 9 people. Females who got an A on the test. What about these 11? Males that got a B on the test, etc. Is the table making sense? So now here comes the question. If one student is chosen at random, find the probability the student was a male. You have to add all those up? Yeah, let me give you, in general, it's always a good idea just to add down and add across, always. So I'll just add down. 16 and 9 is 25. Just grab your calculator. 11 and 18, what's that? 29. 10 and 20, that's 30. And then I'm going to add across also. Because these are the totals, huh? I'm going to add across. That one's a little harder. What's that? 20, 27, 37. And then add across here. 27, 47. So those are the totals across and down. That's always a good thing to do just to help yourself out. You probably won't need it all, but it's helpful. So, and then get the total. So in the right corner, if you can either go up and down or sideways, it'll be the same thing. 7, is it 84? I think it's 84. That's the total amount in all the boxes. All right, so does that help? Let me give you 30 seconds now. What numbers do we need? It's going to be a fraction. What's going to be the denominator? Yeah, so the 84, right? It's always the total number. It's always the denominator in probability. What's the numerator? 37 total males, huh? Is that making sense? And then whatever the calculator says, just hit the buttons. 0.4405. That last spot rounds to a 5, I think. Yeah. Is that good? Is that coming out? Is that making good sense? It's always the total on the bottom, huh? All right, I'll move on. We're spinning the spinner. So, blah, 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 there's some kind of spinner, right? You got like some kind of spinner thing here, and you're going to spin the spinner. What's the probability of that? So the probability that you get a number, and now what's that symbol mean? Greater, right? Greater than 5, or the 5 is less than, whichever way you want to say it. Right? So remember, the symbol has a wide side and a narrow side, doesn't it? You put the bigger thing on the wide side. So whenever you write that symbol, like if I go like this, oops, that's not a good example. If I go like 10 is bigger than 5, or I could write 5 is less than 10. That's saying the same truth 2 different ways, isn't it? right? So the 10 is on the wide side of the symbol. The 5 is on the narrow side because he's the smaller one. Here again, the 5 is on the narrow side. The 10 is on the wide side. So whoever you're putting in the narrow side is the smaller. Whoever's on the wide side is the bigger. So it's saying the number is greater, right? Wide side, than 5. So they want us to have a spinner number greater than 5. Greater than 5. What does that mean? 6, 7, 8, 9, 10, 11, or 12, huh? 6, 7, 8, 9, 10, 11, or 12. Right? Aren't those the numbers greater than 5? And how many numbers is that? 2, 3, 4, 5, 6, 7. 7 numbers out of 12, right? And just divide it on your calculator. What are we getting? 0.5833. So that's the probability when you spin that spinner, you're going to get a number greater than 5. Just over 50%, because just more than half the numbers are greater than 5, aren't they? Makes sense, doesn't it? Does it seem right? A little more than 50% chance? We good? Questions? What is the probability in percent form of randomly selecting someone who does not believe that life exists somewhere else in the galaxy? So 46.3% of Americans say yes, there's life somewhere else. There's alien life somewhere else in the galaxy. So what if you grab somebody at random, what's the probability that they're a no person? Basically is what they're asking, huh? So how we can do it? Exactly. Does that make sense? It's just subtract from 100. So you take 100%, take away the 46.3. Just use your calculator. Is it 50? Yeah, 53.7, huh? It's going to be 50. That's the answer they want here. 53.7. Is that okay? That'd be like me saying, if the chance of rain tomorrow is 20%, what's the chance it's not going to rain? 80%. We all know that, huh? You just subtract from 100. That's all we're doing. The idea here is opposite. So whenever you do, you believe there's alien life or you don't. You believe it's going to rain tomorrow or you don't, right? We're just doing opposite. And so when you do opposite, you just take away from 100, right? That good? All right, how about number 12? A group of people were asked if some people see, it's the future in their dreams thing again. It randomly got that. But I think it's a little different this time. Maybe not. 111 said yes. 368 said no. Find the probability the person chosen random person does not believe. Some people see the future in their dreams. Okay. But I think they didn't have a not. The deal. Okay, so a group of people were asked. So 111 say yes. People see the future in their dreams. 368 say no. People don't see the future in their dreams. So if you grab somebody around them, what's the probability that they're a no person? That's not hard, is it? That's just 368 over whatever the total is. I don't know what the total is. So it's going to be 368. It's going to be the no people over whatever 111 plus 368 is. 368 over 4, 79, yeah. And whatever the calculator says. 0.7683. That's the easy one. Let's go on to number 13. I think that. So on number 13, giving a test to a group of students, the grades and gender are summarized below. So here's another, people took a test. Hey, look, they're doing some of the totals for you. They're kind of helping us out a little bit. And they're saying if one student is chosen at random, find the probability that the student did not get a B. Did not get a B. So okay, so how are we doing? What do y'all think? So if you choose a student at random, what's the probability they did not get a B? How are we going to do that? Yeah, so the probability of not getting a B, well, first off, what's the bottom? What's the total? That's the 80, huh? And then what's the total? So it'd be the number that got A's plus the number that got C's. Not if they did not get a B, and they got an A or a C. So what is that? How many got A's? 28, right? Because that's the total number of A's. How many got C's? 21 out of 80. So that's what? 49 out of 80. Hit the buttons on your calculator. I'm getting 0.6125. How are we doing? Is that making sense? Questions I can answer on that one? Does that make sense? If they didn't get a B, then they're the A and C totals, aren't they? Out of 80.
Yeah.
All is good? Okay, so here again we have a table of pedestrian deaths caused by automobile accidents, and whether the pedestrian was intoxicated, yes or no, driver intoxicated, yes or no. If one of the pedestrian deaths is randomly selected, find the probability that the driver was not intoxicated. That's what I'm saying. So the probability, they want the probability driver not intoxicated. So if you grab one case or person at random, what's the chance you get one where the driver was not intoxicated? Whereas the last one, see how they have the totals already here and here for you in the last one? So if they don't have that, like they did on number 13, it'll be helpful to get your own totals. So let's do that. So I'll do the total here. So what's 53 and 233? 286? 286. And then these two, I don't know. 680, 695, I think. 695 total. Okay, and then on the other side, we want the totals over here also. So that'd be these two added up. I don't know what that is. What's that? 60, 120. And then these two added up, which is some other number. 861 maybe. I'm gonna do that one. Yeah, 861. And so then the lower right corner is the total, which you can do sideways or vertically. It'd be the same either way. 981. So there we go. Okay, so how do we do it? Not intoxicated. What's the denominator going to be? Let's start with that. What's the denominator? Yeah, that's always the total, right? 981. And now they want driver not intoxicated. How many cases was that? Yeah, right here, huh? 861, right? Because that's driver intoxicated, no. There's the total. 861. Is that making sense how we read that table? Right? Because I just added up these two to get the total no, the total cases in which a pedestrian died, but the driver was not intoxicated. That's 861 out of 981. So that would be the probability if you just grab somebody random out of that crowd, or a case at random, you would get that. Driver not intoxicated. So that's 0.8777. It rounds to be. So there's about almost an 88% chance. So about 88% of the time, excuse me, about 88% of the time, when a pedestrian is killed in an auto accident, the driver was not intoxicated. At least if that data is real. Making sense on that?